In this video, we will be discussing an object moving at a constant velocity. The goals of this lab are to use Tracker to create a position versus time graph for a filmed object moving at a constant velocity, create a computational model that predicts this motion using Newton's second law, compare the data from these two trials, and lastly consider a few of the external forces that might affect the results and generate differences between the two groups of data. Before I delve into the observed and computational models, first let me explain Newton's second law and what it claims about motion. In words, the law states that an object's acceleration is directly proportional to the force on the object and inversely proportional to the mass of the object. In simpler terms, the object will accelerate and therefore have an increasing velocity if the object in question has a large force acting upon it as well as a small mass. The converse applies for deceleration. Notice, however, if there is no total force acting upon the object, then the final velocity will be equal to the initial velocity. This is what will be demonstrated in this lab, as constant velocity occurs when no net force is acting upon the moving object. For a quick clarification, we are beginning the lab after the object reaches a constant velocity, not when it is at rest. Yes, some force made the object begin to move to go from 0 meters per second to a non-zero velocity, but because we are only collecting data from when the object is moving at a constant velocity, we can disregard this initial force. For my particular lab, I took a short video of a truck driving on a road. I picked my frames on Tracker according to where the velocity seemed constant to the naked eye. To obtain the initial velocity, I took the average velocity of the first two recorded data points. Although this is not technically the exact instantaneous velocity at t is equal to 0 seconds, the time interval is so small that the value calculated is sufficient. Notice how the two lines on the graph very slightly diverge at the end of the time interval. The blue line, which represents the observed position of the object, is slightly above the predicted position, or the red line. Because the slope of the position versus time graph represents the velocity at any given time, and because the blue line is less steep than the red line at the end of the time interval, we can conclude that the magnitude of the truck's velocity slightly decreased in real life. We will go through a few reasons as to why this might have occurred. As the truck itself was approaching a stop sign, it would be logical to think that the truck's brakes caused the vehicle to decelerate towards the end of the interval. Because the speed is not completely constant, this would explain why the predicted data does not match the observed data completely. In most labs, there is plenty of room for human error. In this particular case, there were many factors generalized for simplicity. For example, I relied on the average values of the truck's weight and height, as they are most likely very close to my situation. In addition, I picked the center of mass of the truck for each frame, which can vary somewhat from frame to frame. Although small, moving the center of mass a little further than is consistent may indicate the truck increased its velocity very slightly. Take note how the position graph has a downward slope. This is due to how I chose my axes. I decided to utilize a traditional graph setup with the positive x and y directions being to the right and up respectively. The truck moves to the left in the video, so it makes sense that the position of the object is becoming more negative with time. In addition, because the change in position is negative, my velocity would also be negative. What happens to the data if I choose a different axis? In reality, not much. If I claimed the positive x-axis was to the left instead of the right, the truck's position would be getting more positive and the velocity would be positive. What is important is that the magnitudes of the numbers stay the same. In short, changing the axes in this way changes the direction of the motion, not the magnitude. Next, let's consider if it is possible to determine every single force acting upon the truck as it moves at a constant velocity. The answer is maybe, but it would be extremely difficult to do so. Now we will consider some of the forces acting on the object. Firstly, the road has a normal force on the truck that is equal in magnitude but opposite in direction to the weight of the truck itself. Because these vertical forces essentially cancel each other out, the truck does not move up or down in the y direction. In addition, the truck is applying a force to the ground, which propels the truck forward as the driver puts his foot on the gas pedal. The force of friction, along with air resistance, however, cancel out the motive force in this case of constant velocity, therefore resulting in no net force in the x direction as well. However, there are more forces to consider that, while small in magnitude, might affect the motion of the object in real life. For example, if the truck is moving on a slightly inclined surface, then the force due to gravity and the normal force are not in opposite directions. This makes totaling the force on the object more difficult, as we now have to consider the components of gravity to calculate the corresponding normal force. In addition, there are many ways friction impacts motion. For example, static friction between the road and the tires causes the truck to begin moving instead of the tires rotating in place. However, there is also a kinetic frictional force opposing the motion as the truck is moving. What is important to understand is that in an ideal situation, even if we do not determine every single force acting upon the object, we can at least conclude the net force, which should add up to 0 in the x and y directions. In conclusion, Newton's second law tells us that when there is no net force acting on an object, it will retain a constant velocity. We also saw that our computational model of the truck's motion is fairly accurate due to the observed motion, but not exactly due to small but significant unbalanced forces in the real world. Lastly, we considered hypothetical questions such as if it would be possible to change the axes of motion or know every single force acting upon the moving truck.